This lecture is a continuation of the previous lecture on time domain analysis. So in the previous lecture, we discussed about the second order system. The transfer function of the second order system is omega n square by s square plus 2 theta omega n s plus omega n square. Here omega n is the undamped natural frequency and theta is the damping ratio. So depending upon the variation in theta, we have four types of systems: undamped, underdamped, critically damped, and overdamped system. Let us look at the response for a second order system for different types of damping and input as unit step function. In this course, we are studying only about the response to unit step type of input. So to solve that, we need to be familiar with some important Laplace transform pairs. So for u of t, it's quite familiar that the Laplace transform is 1 by s. When you have t multiplied by u of t, this will be changing to 1 by s square. When it is t raised to n multiplied by u of t, it is n factorial by s raised to n plus 1. Similarly, if you have e raised to lambda t multiplied by u of t, it will be 1 by s minus lambda, which is the Laplace transform of e raised to lambda t. If t is multiplied with e raised to lambda t, then this 1 by s minus lambda will be squared, similar to this one. When t raised to n is multiplied, you keep the Laplace transform of 1 by s minus lambda as such and modify it according to this formula. So it is n factorial divided by s minus lambda raised to n plus 1. Similarly for cos and sine, it is, remember that the denominator is the same, s square plus b square, but the numerator is s for the cos, and for sine it is a constant b, the same constant b. So first let us look at the response of undamped second order system to unit step input. So this is an undamped system, so theta is equal to 0. So the transfer function modifies as omega n square by s square plus omega n square. The input is 1 by s. So the output response C of s is transfer function into input. Transfer function into input. Now we need to split this into partial fraction to get the inverse Laplace transform of C of s, so that we get C of t. So first let us find partial fraction. So a by s plus bs plus c by s square plus omega n square, since this is a quadratic term. For quadratic term we write bs plus c. For linear term we write just a constant as the coefficient. So solving properly you can get this kind of a solution. So finding the time domain response, we have for 1 by s, the inverse Laplace transform is 1, and for s by s square plus omega n square, the inverse Laplace transform is cos. Because numerator is s, it is cos. Looking at the graph, so this is the input u of t, this is the output c of t. Notice that the output is oscillating in nature, cos signal, without any damping. So instead of a unit step input, if you have a general step input, the output will just be multiplied by the amplitude of the step signal A. So every practical system has some amount of damping in it. This kind of an undamped system is actually an ideal model and does not exist in practice. So second one is response of critically damped second order system to unit step input. So if it is a critical damped system, we have theta equal to 1. So the transfer function simplifies as this. Here theta equal to 1. So this is in the form of a plus b the whole square, s plus omega in the whole square. So since the denominator is linear, When using partial fraction, it will be easy. We have input 1 by s and output C of s is equal to transfer function into input. Using partial fraction, we can split it into this form. So a by s plus b by, if you have repeated linear terms in the denominator, we can write it as b by the first term plus c by the second term whole square. We can solve it accordingly and get this answer. How do we get the time domain response? For 1 by s, it is 1. 1 by s plus a term, it is e raised to minus at. So e raised to minus omega n t. For this one, notice that the denominator is squared. So we have a multiplication by t into e raised to minus omega n t. This omega n is a constant which is occurring here. So this is the response of the system to critically damped second order system. So let us look at the graph. So this is the response for a critically damped system. The third one is the response of underdamped second order system to unit step input. This is the most commonly occurring type of second order system and most important. Theta lies between 0 and 1. This is the transfer function. So the output response is transfer function times input. Notice that you have a linear term and a quadratic term in the denominator of the transfer function. So when using partial fraction, we have to split it into two terms. So the linear term, we have a coefficient a. For the quadratic term, we have coefficient bs plus c. So cross multiply and solve it to get the coefficients a, b and c. Now this denominator is not directly in the form of a plus b the whole square, but we can split it into a plus b the whole square plus another term. To do that, we need to look at the first two terms, and in the second term, take the half of the second term so that you can express it as s plus theta omega n the whole square. But when you express s plus theta omega n the whole square, you get the term as s square plus 2 theta omega n s plus theta square omega n square. But that is not the term which is given here. So what we can do is we can add and subtract theta square omega n square to express in a convenient form. So in the second step, notice that we added and subtracted theta square omega n square. So now the first three terms can be grouped to obtain s plus theta omega n the whole square. So the first three terms becomes s plus theta omega n the whole square, and the remaining two terms can be grouped to obtain omega n square into 1 minus theta square. This term omega n square into 1 minus theta square can be again expressed as omega d square, where omega d is the damped frequency of the system. So now onwards, remember that the term omega d is nothing but omega n into root of 1 minus theta square. So the response now becomes 1 by s minus s plus 2 theta omega n by s plus theta omega n square plus omega d square. This term can be split it into two terms. One is s plus theta omega n by denominator. The second one is theta omega n by denominator. So this is to find the inverse Laplace transform of this function, we have to refer to these standard LT pairs, standard Laplace transform pairs. So if you have only s in the numerator and s square plus omega n square in the denominator, the Laplace inverse transform is cos omega 0 t. If it is a constant by s square plus omega n square, you can express it as sine omega t. But if you have s plus a constant added to the s, then it will be e raised to minus alpha t cos omega t, and here it will be e raised to minus alpha t sine omega t. So referring to these LT pairs, you can simplify this expression. This is in the form of a cos omega n omega dt multiplied by an exponential, and this is in the form of a sine omega dt multiplied by an exponential. So let us look at the time response. So now time response is 1 minus e raised to minus theta omega nt cos omega dt. So this is the cos term, and for the sine term we have e raised to minus theta omega nt sine omega dt. Then you have the constant theta omega n already present here, and omega d we have divided by omega d to express it in the form of sine. Simplifying further, we can express it as shown here. Now notice that here we have replaced the omega d by omega n into root of 1 minus theta square. So now this is the simplified expression for the time response. This expression can be further simplified by including an additional substitution. So if you look at this right angle triangle having an angle theta, and if the hypotenuse is root of 1 minus theta square and adjacent side is theta, we can get sine theta equal to root of 1 minus theta square and cos theta equal to theta. So these two terms are available in our expression shown here. So now replacing this term by sine theta and this term by cos theta, we obtain this equation. Now this is in the form of a sin A cos B plus cos A sin B form. So according to trigonometric equation, we can express it in as sin A plus B form. It can be theta plus omega dt or omega dt plus theta. Both are the same. So this is the final expression for time response of a second order system, underdamped second order system to unit step input. This is a very important equation. So if it is a step response, just multiply this answer by A, which is the amplitude of the step signal. Now the last one, which is the graph of the signal. So the input signal is unit step and the output is a underdamped system. Notice that the system is initially oscillatory and then damping. So response oscillates before settling to a final value. So next is the response of overdamped second order system to unit step input. Theta therefore is greater than 1, and this is the transfer function. So for this system, we find the roots of the denominator of the transfer function and express it as S1 and S2 for simplicity. So now using S1 and S2, we can factorize the denominator as shown here. S1 minus S minus S1 into S minus S2. So the output response will be this transfer function multiplied by input. So since these three terms are linear, we can use partial fraction as A by S plus B by S minus 1 plus C by S minus 2. We get this solution by solving the partial fraction. Now for simplicity, we can find out omega n square by S minus S1, S2 and omega n square by S2 minus S1, which we obtain as this form. Both will be the same value. We can substitute both these values in equation number 1. So the simplified form will be shown here. So these two terms have common omega n by 2 into root of theta square minus 1. So the output is given by this equation, where we have taken out the constant term, and this Laplace transform simplifies as e raised to st by s1, and this one the inverse Laplace transform simplifies as e raised to s2t by s2. S1 and s2 are constants here, which is shown here. Now going for the graph, for the Overdamp system we have the graph shown here. And notice that when theta is greater than 1, you have the curves which is less than the critically damped curve. So this somewhere here is a critically damped curve. So these curves are less than that. Thank you.